burgers?
It depends on what you buy.
All right.
Put a food wish list out on Moodle. Oh, by the way, these are just what I like. You know, just saying. Some of you guys know what this means, others don't. That's cool.
I always do the reading.
Or you could create a program in which we have to hack to find.
Yeah, there we go.
Yes.
I keep forgetting about the transition between 310 and 430 or 440, and so going back and forth, I'm like, wait, which is? Oh yeah, that's the one about hacking and stuff. That's not about
Yeah, the
hacking
hack
and
class.
stuff. I took a hacking
Clearly
class here.
hackless. Did you take ethical hacking?
Yeah.
How was that?
It was interesting. I took it for, you know, its informative aspect.
Alrighty.
Events and stuff like that.
So you can see that the recorder is on, and I am going to start cisp310.
I
Okay.
didn't do it though. This on the computer. It's just like, hey, blue screen to that.
Alrighty.
Because that's
cisp310. So what we'll do today is we're going to focus on adding. Okay, something as simple as just adding. And you will see, we'll talk about binary adding, and we'll also talk about how to use logic gates to perform those operations. So before we get there, we'll kind of go back just a little bit to talk about low-level representation. So it's this particular slide, and I'm just going to go through all of these pictures really quickly. Yep, go ahead.
I think your mic's not on.
Mic is not on, but it's still recording because I'm
Alright,
standing
that was
close
good.
enough to it. And now it's on. Oh, yeah, some people call that the... This is not my words, okay, so don't blame me for that, okay? Some people call this the God voice. I'm not quite sure which voice, but it is a voice. It's amplified, which is called that.
The all-seeing voice.
Yes. So here, we just kind of quickly go through the physical devices. We have already talked about vacuum tubes, okay? So, and if you want to find out exactly how a vacuum tube works, okay, in terms of, this is the heating element, and then it emits electrons. This is how a gate works, whether electrons can pass through or not. Just go to Wikipedia. They have a pretty good explanation of how vacuum tubes work. Transistors, integrated circuits. We talked about the exponential shrinking, in this case, of transistor size. Okay, it is still ongoing, and there are many people, throughout time, saying, "Oh, this cannot continue forever. It has to end like this year. Okay, we're close to the end, and so on." But at this point, it is still going. Okay, if you look at how many transistors we can pack onto a processor, okay, it is still going. Intel now has to go to 3D designs where they put transistors on the side of a channel. Okay, they have to go through all kinds of weird tricks to do it, but they're still doing it. Okay, they're still continuing Moore's. This is called Moore's. What is the name of that?
Moore's law.
Moore's law.
I believe so.
Okay. Oh, but it's still going. But to us, it's not important, what type of transistor we are dealing with. We just have to understand they are only valves. Okay, they're basically devices where you can open or close, let it flow, not let it flow. And then two more requirements. The very same thing that you use to turn it on and turn it off is the same thing as the output of the valve. Okay, so it's not like a light switch. You turn it on and turn it off manually. But when you turn it on, it let electricity go through. So it's more like a relay where you can use an electrical signal to turn it on and turn it off, but in return, it also turn on and turn off another electrical signal, possibly to another relay. Is that okay? And then the other requirement is you have, well, it may not be an actual requirement, but it's nice to have two types of switches. We call it normally on and normally open and normally connected. Okay, it basically says if the input is high, are we turning on or turning off the output? Okay, and in this case we have two that turn on when the input is low, and then we have two that turn on when the input is high. Okay, and using this arrangement, we can now work this out. Okay, last time we worked out the logic of this particular circuit diagram and say that, hey, it does exactly the same thing as a negated conjunction. Okay, remember that conclusion? Okay, we use a truth table, look at that thing, go like, oh, this is negated end. And from a single design of negated AND, we also went through the mathematics to come up with just regular NOT. Okay, this is regular NOT, this is disjunction or, and this is conjunction, which is AND. Okay. In other words, the conclusion is now we can go from transistors to logical operations that we are familiar with. That's the bottom line. Okay? You don't have to use transistors. You can use relays if you want. Okay? You can use a bunch of relays, lay out in a circuit, and we can actually implement negation, conjunction, and also disjunction. That was the conclusion. Are there any questions about that conclusion? Okay. And then we quickly went through the concept of representation of values. Okay, how we are separating the concept of a value from the concept of numbers. So basically, the idea is the quantity of items, there are 7 in this picture, is a quantity, is a value. Okay. But how we represent that value is we can choose. So we can use 7, spell it out. We can use the digit 7. We can also use 111 in base 2. We can use 21 in base 3. We can use 13 in base 4, and so on. Okay? So these are numbers. In other words, numbers are really just representations of values. Are there any questions about this picture or the concept about values versus numbers? Okay, no questions? Okay. So this means if we by any chance encounter an alien species, the chances of them expressing pi as 3.14 blah 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 is very slim. Because why do we use base 10? Because we got 10 fingers, which in hindsight is actually very unfortunate. Okay? Well, I will explain that along the way. There will be multiple classes where I will say that again and again. Well, 10 is not a really good number as a base of a number, because 10 is 2 times 5, right? So it's not really it's not a prime number. As a composite number, it is not a power of a particular base either. It's not 2 to the power of 4, which is 16, right? Or 2 to the power of 3, which is 8. So it's kind of like a random-ish number that we use as a base. Okay. We feel comfortable with base 10 only because of one reason. What reason is that? It's because I think the youngest student in this class probably is 16, 17. Yep.
It's because we got tired of the Greek numerals, and so we decided to make it a little convenient.
10 is not convenient. That's the bottom line.
I don't know,
Greek
I didn't
numerals
decide.
are still base 10.
It's kind of base 10, yeah. It does roll over, when we get to 10. Okay, so we talked about base conversion. Okay, we talked about base conversion. We talked about base 2 conversion, converting a value into so that it can be represented in base 2. Even fractions, okay, even small values smaller than 1 can still be represented as a sum of powers of 2. Just like we express decimal numbers as a sum of powers of 10, right? Because what is 0.25? 0.25 is 0.2 times 10 to the power of -1 plus 5 times 10 to the power of -2. Okay? So that concept doesn't change. Doesn't matter what base you're using. It is still a summation of powers of a particular base. So we finished this example in class. I think I've used another value, but nonetheless, it is the same stuff. We have the lab activity, which is setting up a Linux box and stuff like that, and I think most people got through with that. Logisim is good. We'll come back to that one, but at this point, we are going to move on to binary adding. You can see some of these items are grayed out. You cannot see the grayed out items because I do not use that anymore. I'm replacing some of the items with the quiz form reading material. because I just want you guys to kind of think a little bit at the end of each slide before you move on, okay? Just to make it more interactive. And that way I can also tell who read something and who does not read a single thing throughout the whole semester. It will all be summarized on the grade sheet very nicely and neatly. And then at the end of the semester, I can make a correlation between the actual grade of people versus whether they go through the reading material or not. Yeah, we don't cheat. We just lack integrity. Now I would catch those people too. But I'll put it the other way. Those people would catch themselves. I just put a trap there. I didn't push people onto the trap.
You just put it at the right spot.
People just willingly walk onto it. Okay, so let's go to binary adding, which is a really fun, quiz. 31 people. Well, there are 31 attempts, but doesn't mean that there are 31 people who participated, because one person can participate or attempt multiple times. You don't have to raise your hand, okay? I have not even checked, who tried it multiple times, which is not a problem, okay? You didn't get it all right the first time, do it again, okay? Try to figure out what went wrong the first time, but at the most, 31 people did it. You just look around you. Do we look like we only have 31 students in this class? So that means some people did not do it. So this is a flag, okay? Do the reading material, okay? It's important. All right, so I'm just reading out the questions, and I'm not going to give you the answer at the end because I still want you guys to kind of figure it out by yourself. So we talk about base 10 adding first. Base 10 adding, I mean, who need to know that? We already know that. 2 plus 4 is 6. Does anyone want to dispute that? Does anyone want to claim that that's not true? Well, that's true in base 10. What about in base 5? In base 5, 2 plus 4 is
14?
1, 1. Because there's 1, 5, and then there's 1, 1. Okay? So once again, we know that 2 plus 4 is 6, only because we have been taught base 10 our entire life. Well, until today. So today is a very good and interesting day where we'll learn and say, hey, it's not all base 10. Yep.
So if we were hypothetically using base 5 and you see that number 1, 1, base 5, would it be correct to read that as 6? Or should we read that as 1, 1?
We'll read it as 1, 1, base 5. Because when you say 1, 1, as 11, 11 is a value of, a certain quantity, a certain number of items. So we don't want to read it. We don't want to read it as 11. So we want to still read it as just 1, 1, but we have to specify the base because it's not base 10. Our normal assumption doesn't work anymore. Okay. Yep.
I get what you're saying, but if we were to specify that it's base 5, even though we set it as 11, would that be incorrect? Even though we specified specifically that it was base 5.
Because 11 as an English word is associated with the quantity of 11. And yet 1, 1 in base 5 does not specify that quantity. It specifies what we know as 6 as a quantity. It's just that 6 has a single digit to represent it in the numerical way. But 11, there's one single word to describe the quantity 11. But when we write it as digits, we need 2 digits to write out that quantity. So we don't want to spell out 1, 1 in base 5 as 11. We just say it's 1, 1 in base 5. Is that okay? All right. So the next question is, what is 6 plus 7 in base 10? How do you know it is 13? Because as kids, we play with blocks, right? So there's something that has a block length of 6 units. There's one more thing that has a block length of 7. We put those 2 blocks together. It's kind of long, right? and then we put a block that is of length 10 next to it, and say, oh, okay, it's longer than the block of length 10, whatever unit you choose to use. And how much is left? 3. Oh, okay, now we write it as 1, 3, because it takes one long stick that has 10 units, and then there's 3 sticking out, and that's why we write it out as 1, 3. I'm pretty sure most of you don't remember how long it took you to remember all the rules for addition. Can anyone just kind of guesstimate? How long did it take for a kid, okay, today, to learn that, I don't know, 8 plus 7 is 15, 8 plus 8 is 16, and so on?
First grade?
Yeah.
It depends when you start teaching.
One school year at the very most.
First grade.
Assuming
First
they're not
grade,
a special
yeah.
needs.
Sounds about right. First grade, second grade-ish. You learn about first grade. You learn about addition, and then you learn about subtraction. I think by third grade we learn about multiplication. But each one is a table. Okay, it's a table that we memorize. Okay, because at this point, people look at 6 plus 7. They know it is 3 with a carry of 1, without even thinking in blocks. Well, let's hope that we don't have to think in blocks anymore. But we have it memorized. But there are many, many cases that we have to remember in order to get all of those down. Okay? So the answer is 13 is correct, okay, without any base specification. It is just a base 10. So 13 is right, but what I want to use is to specify that as 3 with a carry of 1. Because if I say it is 13, yeah, it's still correct, but it doesn't lend itself to multi-digit addition. But if I say it is 3 with a carry of 1, now I can actually do multi-digit addition because I have the concept of a carry. Is that okay? Okay. All right, let's move on. So the carry is there because in base 10, a single digit can only represent a value from 0 to 9. So if the sum is more than 9, okay, then we have a carry to the next digit. Because the next digit takes care of multiples that are 10 more than what I'm supposed to take care of. Okay, that's how a number system works. So I'm pretty sure most of you do not need to be reminded what a carry is, why it is important in addition and stuff like that. So I think for base 10 we are done. So the question here is in a base 5 system, what is the largest quantity that can be represented by a single digit? Yeah, exactly. Binary numbers. So with binary numbers, it's base 2. Each digit can only be a 0 or 1. A value is represented in base 2 is basically a sum of powers of 2. Okay, which is something that we already know because in base 10, this is 163 because I don't give you a subscript something, so it is just in base 10. So 163 as a base 10 number is 100 plus 60 plus 3. But what is 100? 100 is 1 times 10 to the power of 2. I'm skipping to the third line. The 60 is 6 times 10 to the power of 1. And then the 3 is 3 times 10 to the power of 0. I want you to see the pattern. Okay, this is not the first time. Okay, in the previous slide, I think that we had something like that already. We can use the same pattern for binary numbers. But in binary numbers, this is not good. This is supposed to be a subscript 2, not a plus 2. But basically, this is a base 2 number, and I break it up into the individual digits, like that. And then for each digit, if you look at 1 followed by 6 zeros here as a base 2 number, it is representing 2 to the power of 6, which turns out to be 64. This one is 1 followed by 5 zeros. It is representing 2, which is the base, to the power of 5, which is the number of zeros. And that turns out to be 32. But since we have 0 of those, it doesn't contribute to the sum. Are we doing okay so far with this breakdown here? Okay. So what I want you guys to see is a parallel between how we understand base 10 numbers and how we understand base 2 numbers. Basically, the same way. Okay, there's not a whole lot of difference. And numbers with a decimal or binary point works out the same way. It's just that 0.1 here is 10 to the power of -1, and then 0.04 is 4 times 10 to the power of negative 2. So basically, on one side of the decimal point, we have powers to 0, 1, 2, 3, and so on. And then on the other side, we have negative powers of 10. Or whatever base you choose to use. Okay, so base 2 numbers will work out the same way. So now the question is, what is the value in base 10 represented by 101.01 in base 2? So I'll let you guys work that out. So this is not, so now we're going back to addition because I want you guys to understand base 2 first, and then we come back to addition. So in base 10, we have, when you learn addition, potentially there are 100 items in a table for you to memorize. And of course, we know that there are not really that many. Because when you look at this table, okay, so we have 0 all the way up to 9, 0 up to 9, and then each cell is really the sum of the number represented by the column and the number represented by the row. Okay? So if I pick out one particular one, let's say we have 6 over here and 7 over here. Okay? So when we have this particular cell, it is 3 with a carry of 1. But this table is a 10 by 10 table. There are 100 items. Now there are some trivial items. The first row is trivial because 0 plus anything is whatever that something is. Something plus 0 is also trivial. Then we have 81 items left. Of the 81 items, because addition is commutative, so it is symmetric, we still have half of 81 items to remember, which is a lot. Okay? Anyone who has young children will probably remember that it takes quite a bit of time to get it all right. Okay. What about binary numbers? There are 4 cases. Because instead of having 10 possible values for each digit, we only have 2 possible values per digit. So we only have 4 cases because it's a 2 by 2 table. 0 plus 0 in base 2 has a sum of 0 and a carry of 0. Are there any questions about this? Nothing plus nothing is nothing, and I got nothing to carry. Any questions? Does making it base 2 make any difference? Okay, all right. 1 plus 0 in base 2 has a sum of 1 and no carry. Is that okay? Because we can still represent 1 using a single digit in binary. Is that okay? Well, this one is symmetric. This is the other side of the previous one. 0 plus 1 in base 2 has a sum of 1 and a carry of 0. Any questions about that? So the only one that's tricky is 1 plus 1. So 1 plus 1 is the only one that is tricky because the value 2 cannot be represented by a single digit in base 2. So what do? Well, we just say that, hey, the sum is now exceeding what I can represent using a single digit. We have a carry of 1. Let the next digit take care of that part. Oh, but if the next digit is taking care of 2, what is left for me to take care of? A 0. Okay, so that's why 1 plus 1 in base 2 is 0 with a carry of 1. In terms of concept, it's kind of like saying 5 plus 5 is 0 with a carry of 1 in base 10. Because you got just enough that you cannot represent the result quantity in one single digit, so you have to have a carry. But once the carry takes care of that part, there's nothing left for this particular digit to take care of. Is that okay? How long will it take you to memorize those 4 items, of which 3 are trivial? 5 minutes? 10? Don't you think if you present this in elementary school, all the first graders would just cheer?
By comparison.
Hmm?
By comparison.
By
They're
comparison.
still learning.
Well, it's easier. It's much easier. All right, so that's it. Those are the 4 rules of binary addition. So in this case, the question is, what is the purpose of carry-in addition? Okay, so there are 2 answers, and one is obviously wrong. To indicate the value cannot be represented in base 2 regardless of the number of digits, or to let the next, put in parentheses, more significant digit handle the excess of what one single digit cannot represent. I'll let you guys choose. Okay, so now the next question is, okay, so we have the binary addition table, okay, expressed in the sum and also a carry. Okay? When there's no carry, you can always say it's a carry of 0. Okay? That works. So now the question is, well, those are still arithmetic operations, and yet we do not know how to do that with a computer, because a computer is made out of transistors. And with transistors, we can do logic gates. Remember the logic gates that we did in the previous class? So we know how to use transistors to make up logic gates, but we don't quite know how to use transistors to compute, to calculate, to add, to subtract, and so on. So if I have a way to turn addition into logic gate operations, then I can actually perform addition using logic gates. Would that be a desirable outcome? Yeah. And because now we can actually have computers that can do calculations, computations, and so on. Okay. So that's what this slide and the other few slides are about. So what we'll do is we are going to define 2 functions. The first function is C for carry. Okay. So this basically what this means is the carry of adding 0 to 0 is 0. The carry of adding 0 to 1 is 0. The carry of adding 1 to 0 is 0. The carry of adding 1 to 1 is a 1. Does it sound redundant? Haven't we talked about this already? Just in a different way?
Yeah.
Yep, absolutely. I just turned it into a more formal representation using a function. Okay? Not to be confused with function from the previous class. It really is a function too, but this is not in the context of function in cisp 440. It's just a normal function. Okay? All right. So the next question is there a logical operator that has the same behavior as the carry function? You give it 0 and 0, it gives you a 0. You give it a 0 and a 1, it gives you a 0. You give it a 1 and a 0, it gives you a 0. On the other hand, if you give it 1 and 1, it will give you a 1. And, logical and, okay, conjunction.
Table, right? That one table, the truth table?
Yep.
The truth table, exactly. Conjunction, we'll do it. Okay. Oh, wait, hold on a second here. Can that be done with a logic gate, or multiple logic gates, or transistors?
What?
Conjunction.
Yeah.
Yeah, we showed it last time. Okay, so to figure out the carry of adding 2 binary digits, we can do it with transistors. Good. Next slide, we'll talk about something just a little bit more difficult, but not too bad. So I'll leave it up to you to answer this. Okay, the result, okay? So the R is going to represent the result of adding bit X to bit Y in this case. So X can either be 0 or 1, Y can only be 0 or 1, and then the output can only be 0 or 1, okay? So from 2 slides ago, we know that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. The only one that was kind of tricky was 1 plus 1 is a 0 in base 2, because the quantity 2 cannot be represented using a single digit. And yet a carry will take care of the value 2 altogether, so there's nothing left for this digit to deal with. Is that okay? So the first paragraph should really be redundant because we already know that stuff from 2 slides ago. Is that okay? So the next question is, can we use a single logical operator to do this? And the answer is yes, we can, but it is not an operator that we are used to. We don't use it very often as a logical operator. It is exclusive OR. Okay? And exclusive OR can be written as a cross with a circle around it. Okay, so it's just kind of like an add but with a circle around it. Okay? That's one way to represent it. What if I don't give you exclusive OR as an operator? Can we define exclusive OR using the other logical operators?
Sure can.
And the answer is yes, it's just kind of clumsy. Okay? So the clumsier way to do this using just conjunction and disjunction and negation is like this. Okay? If I want to express x exclusive or y, okay, I can rewrite it as a conjunction of x and the negation of y, negation of x, conjunction y, and then we take these two conjunctions and then we use a regular or between them. It will do exactly the same thing. It's just kind of long and clumsy, but it will still work. Are there any questions about this? Okay, let's focus on the right-hand side of this equality, of this equation here. Let's focus on this side here. And can we implement every single one of these operations using transistors? Okay, the little inverted V thing is conjunction. Can we do conjunction using logic gate? Can we do it using transistors? Let's go one level lower. Yes, we can. The V symbol is OR. Can we do an OR using transistors? Yes. The little bar with a cliff thing, that's a negation. Can we do negation using transistors? Oh, so we can do exclusive OR using transistors. But guess what? Those are the only two things you need to do binary addition. Does that make any sense? Because we have to deal with the result of the addition, we have to deal with the carry of an addition. Now we know how to do both of those using logic gates, which implies we can do both using transistors. Is that okay? All right. So here I just wanted to give you a few more options of notations because some of you who are transitioning into computer engineering instead of computer science will probably see these equations or see this form of equation a little bit more. Okay, let me just go back and point to this one. This is what mathematicians do. Okay, mathematicians would use these symbols. We have conjunction, disjunction, and negation. Electrical engineers do not like writing a lot of stuff, so we like shorthands. Multiplication is the shorthand of conjunction. Addition is the shorthand of disjunction. Negation is just a bar on top. So that's why you see x, y bar. Well, the bar is right on top of y. Is the conjunction of x and the negation of y. On the other side of the plus, you have a bar on top of x, which means the negation of x, and then times y. Remember, multiplication or times is the same thing as conjunction. So we have the conjunction of the negation of x and y. We take each partial result, and we use exactly the same rules. Multiplication has priority over addition. So we take the result of the conjunctions, and then we apply the disjunction between them. And that's why it looks cleaner, okay? I think it really looks a lot cleaner because it's more compact, okay? But that's what electrical engineers use as a notation instead of the mathematical notation. Just want to make sure that you guys can read both of these notations. Okay. But the end result is still the same. The end result, which is what I want to do, is to come up with a logic gate configuration that can do the result of an addition. So this is great because now we know how to do base 2 addition using just logic gates, and everything can now be translated into transistors. Any questions up to this slide? I have a question. Well, we can only do base 2 calculations at this point. What if we have to deal with values more than 2?
We convert it to base 2, apply this, and then convert it back to its original base.
That's not the.
That's not what he's asking.
Well,
You mean
I might be. The question itself may be ambiguous, but that's not what I intended to ask. Go ahead.
You mean if our value is greater than 2?
Exactly. So someone may complain and say that you have only been talking about zeros and ones, but what if we have to deal with values that are more than zeros and ones?
We'd have to break them up in sections.
We have to have multiple bits, right?
Yeah.
Is there a limit inherent to base 2 numbers where a particular value cannot be represented? We are only talking about rational numbers. Nope, there's no inherent limitation. Yeah, it just takes more and more units, right? It's no more and no less than base 10 numbers. Okay. All right. So why can't base 10 addition be implemented easily using logic gates? Well, there's something about binary numbers and Boolean values that kind of really jive with each other. So you kind of have to know why. Okay? With Boolean values, how many values are there?
Two.
True, false, right? With binary numbers, how many values can you represent using one single digit? 2, 0, and 1. That's why they kind of work out together. Okay? Base 10 doesn't fall into that category. Multi-digit addition. This is a rather long slide. This is my attempt to spell out how to add 67 to 18. Okay, but I use one particular rule just for the carry. Okay, so the way to read is without the lines, it's a little bit harder to read. 7 plus 8 is 5 with a carry. That's why there's a 1 here. 6 plus 1 from the original numbers is 7, but I did not even bother to write the 7 as a partial answer. But 7 plus 1 is 8, so this is how we end up with 85 as a base 10 number from adding 67 to 18. Are there any questions about the way I write this out? Because that's kind of weird. I didn't put in the lines. Is that okay? Okay, all right. So the next one, just kind of write out the, I use even more rows because I use the partial result. So in this case, we have 7 plus 8 gives me a partial answer of 5, but already a carry of 1. Because this is the least significant digit, there's no carry from any previous digits. So that's why 0 is a carry. 5 plus 0 is a 5. So that takes care of the least significant digit column. For the next column, we have 6 and 1 coming in from the numbers themselves. 6 plus 1 is 7. 7 plus 1, this one is the carry from the previous column, is 8. So I just spell it out even more. Are there any questions about this particular base 10 addition? Nope? Yes? Kind of? Nope? Okay. Next slide. Multi-digit addition. Okay, because I want to point out that there are multiple ways to end up with a carry. The least significant column is still the same as last time. 7 plus 8 is a 5 with a carry. So this time, this carry comes from the original numbers. But then, in the next column, we have 3 plus 6 being 9, okay, which does not result in the carry. But the 9 added to the carry results in a 0 and a carry to the next column. So I just want to point out the carry can come from the first part of the addition or the second part of the addition. Is that okay? Yep.
Now that you're showing that, it looks exactly the same as like if you would, pretty much add numbers like, like the way, the old school way. Pretty much. Yep. You put a carry
I just spell it out even more. Yep. This is like really, really spelled out. But since I do it in base 10, you guys understanding how it works? Okay? So now we do it in base 2. Alright, so now we do it in base 2. We have 1 plus 1. So the number x is 101. The number y is 011 in base 2. Those are the numbers that I'm adding. I have to do it digit by digit. 1 plus 1 gives me a 0. That's the result. But at the same time, it gives me a carry of 1. So that's why we end up with a 1 here. Okay? This 0 from the sum of 1 and 1 is added to, this carry from the previous digit. But since I don't have a previous digit, it is a 0. 0 plus 0 is a 0. Is that okay? Next column. 0 plus 1. 0 plus 1 is a 1. It doesn't give me a carry just yet. But this 1, which is the partial sum from the numbers themselves, added to the carry from the previous column, gives me this particular 0, which is the final result of this column. But at the same time, now I have a carry to the next digit. Is that okay? Okay. So now to the most significant digit. We have a 1 plus 0 from the original numbers, which results in a 1. And then we have this 1, which is the partial sum, plus this one, which is the carry from the previous digit. And the result of 1 plus 1 is 0 with a carry. Now, when we're dealing with 3-bit adders, we only have a 3-bit result. So that's why that extra one that is being highlighted right now is not considered a part of the sum. It is just stored somewhere else. We just have a leftover carry of 1 somewhere. Is that okay? Because in binary addition, whatever bit you are using as an adder, you will have exactly the same width for the numbers being added, but also for the result. Okay? Yep.
And the fact that it's being disposed, is that like a security issue?
Sorry?
Would that be a security issue?
No, it's not a security issue. This carry is not really lost. It's just not being utilized or being stored as the result of the addition. Okay. So this is 3-bit addition. So now we make it even more general. Okay, so I'm basically saying x is a binary number. It has 3 bits. I don't know exactly what these 3 bits are. I just want to call them A, B, and C. So A itself can be a 0 or 1, B can be a 0 or 1, C can be a 0 or 1. Is that okay? I'm using 1 letter to represent each bit position. Same thing with Y. Y is a 3-bit number. I don't know exactly what is the value or what is the number, so I'm going to use D, E, F to represent each and every single digit of this particular 3-bit number. Are we okay? So I'm using A, B, C, D, E, F to represent the 2 numbers in binary that I'm adding. Because what I want to do is to work out the actual math. Okay? In general, this 0 is here because it is the carry from a less significant digit. So what less significant digit? This is the least significant digit. So that's why it is always a 0, because we don't have a less significant digit to contribute a carry of 1. So that's why we can stick a constant of 0 here. Are we doing okay so far? Okay. So from the first addition, what we do is we add bit C and bit F. The result will be here. The partial result of adding C and F is going to be in the question mark that I have highlighted. Is that okay? The carry of this addition is going to go here, right? Because it is a carry to the next column. Is that okay? Whatever this is, okay, which is the partial result of adding C and F, is going to be added to a 0. Then the result of that is going to be here. Is that okay? So to spell out all the equations, now we have the bold-faced items are new. Okay? So C plus F is RCF, okay, the result of adding bit C and bit F. CCF, the next column, is the carry of adding C and F as individual bits. Is that okay? And the final result of this entire column is the result, okay, let me just point here, is the result of adding 0 to the result of adding C and F. But this is redundant because adding 0 to anything doesn't really do anything. So I just simplify the whole thing to just RCF, the result of adding bit C to bit F. Any questions? Okay, no questions. And we are now pushing the equations 1 step further to the left-hand side. So the bold-faced ones, once again, are the new items. This one is new. Okay, it wasn't here. It was just a question mark here, and now I turn it into RBE, which is the result of adding bit B to bit E. Any questions? It's just a partial result. It's not done yet. This is still the same thing as before. It is the carry of adding C and F. Maybe a 1, maybe a 0. I don't know for sure. Depends on what is C and what is F. This is the result of adding this bit, which is the partial sum of B and E, and the carry bit of adding C and F. So you can see the component of this particular result is this guy here, which is now here, and this guy here, which is now here. Are there any questions about this particular bit? which is the final result of the second least significant column. The notations is a little bit tedious, but the concept should not be. Yep.
So like on that last row right there, so you're taking R and C and you're getting the results of that. That's why you're putting them in the parentheses, right?
Correct.
Yeah.
Yep.
That just looks out like, you know.
Yeah, it takes a little bit of counting of parentheses to know what is inside what, but the idea is, we are just adding this bit with this bit, and that's the result of the adding these two. But the most important part is, what is going to contribute to this carry? Because now we have two sources that can contribute to the carry of the most significant digit. Think about this cell here, okay? This cell here. It can be the result of adding B and E. In other words, if B is a 1, E is a 1, that will make a carry, right? A carry of 1. On the other hand, if this particular bit is a 1 and this particular bit is also a 1, it will also contribute to this column. Is that okay? So now the question is, I have two ways to contribute to that one single cell. How am I going to combine those two things? That's the question. Well, you have your usual logical operators, right? Because each one is either a 0 or 1, so we only have so many ways to combine two binary numbers into one. And the result is actually a regular OR. Just a regular OR is fine. In other words, if B is a 1 and E is a 1, sure, this is going to be a 1, make this entire expression a 1. On the other hand, if the result of adding B and E is a 1, and the carry from the previous column is also a 1, fine, make it a 1 too. If one of the sources is a 1, make the result a 1. Just a regular OR. Doesn't have to be an exclusive OR, just regular OR. Is that okay? Haven't we illustrated this in the previous slide in base 10 addition? Remember in the base 10 addition examples, I showed you that the carry to the next digit can be because of the partial result of the numbers themselves, but it can also be the partial sum and a carry from the previous column that can make a carry of 1 to the next digit. It's the same thing. We just have to combine those two sources with a regular OR. That's all. Are there any questions at this point about what we have talked about?
Just, C, F, B, E, just kind of.
It takes a, yeah, but this is not bad yet. Okay.
Yet?
Not yet.
Not yet?
So the last one. Okay, so now we have resolved this. Okay, we use a regular OR. I use double bar, which is a C way to represent disjunction to indicate this result here. And this is the whole thing. Since you said it's kind of clumsy, now I show you something that's even worse, right? Okay, the worst part here is the addition to this. It will be the buns that are in boldface. So this is new, this is new, and this part is new as well. Okay. But if you think about it, it's not really that bad, okay? Because if you look at this one here, is over here. You look at this entire thing, which looks like a big mess. It's this entire thing here. Is that okay? And what about this guy here? The first item is the carry of adding bit A and bit D. That makes sense, right? Because if A is a 1, D is a 1, I immediately have a carry that is kind of like the leftover hanging, carry. On the other hand, what about this mess here? I mean, this looks like a really big mess. It's not really that big of a mess, okay? It is the carry of adding this particular bit to this particular bit. It's really literally, it's just copy and paste. But the concept is you have to combine the previous column carry with the current column partial sum to come up with the carry for the next digit. That's it. That's the pattern. Are we still doing okay so far with these, symbols, equations? Question. Do you think this took me a lot of math, derivation, and stuff like that? Or do you think it's just a whole bunch of copy and paste? Just a whole bunch of copy and paste, exactly. Okay, so what I do is I just do a bar bar here. I copy, I put a CAD, here, and then I just, do a C, open paren, comma, close paren, copy, paste, copy, paste. So the only trick is you have to know where you're copying from and where you're copying to. So when you're reading this, you just have to know the pattern, okay? Where is this chunk coming from? You have to know where it's coming from. Are we doing okay? Have I introduced anything that you did not know about addition? Absolutely not. If you're thinking this class is awfully boring, you're absolutely right. It should be. You should feel this class is really, really boring at this point because Tech has not taught us anything new, except that base 2 is better than base 10. Right? Sort of. Because everything else is really just symbols being copied around and defining what is R, defining what is C, and all kinds of stuff like that. So here's the question. The question is, if we expand this table to handle 64-bit addition, what is the potential problem? This is only 3-bit.
It's gonna be long.
It's going to be long. And somebody is going to copy and paste something in the wrong place. The concept is easy, but it's easy to make a clerical manual mistake and you end up with the wrong equation. Can you imagine Intel making a 64-bit processor, somebody make a mistake in the adder because of copying and pasting the wrong part?
It's gonna burn up.
It's not going to burn up, it just gives you the wrong answer. And remember, adding is one of the most basic operations, okay? Because you can define multiplications using addition, right? Shifting and multiplying. So if you get addition wrong, there's nothing this processor can do right. Okay, so you get to answer this question. So the other way to do this is what we call carry ripple. But before we talk about carry ripple, I'll just take one of these equations. This one is taken straight off of, let me go back to the previous slide. Okay, so take a look at this one, CBE plus blah, 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 okay? So this is taken right out of here. Okay, so I'm looking at one single bit position here and say, can we express this mess, okay, using as little time as possible? I didn't say gate. I did not say transistor. I said time, okay? How can we compute the highlighted expression with as little time as possible when you implement everything as transistors?
You simplify.
Okay, you can simplify, you can expand, distribute, and stuff like that. So let's take a look at this one just the way it is right now. Okay, how many levels of functions do we have? Okay, let's just count. Okay, we got, this is one level, right? Both of these are one level. That's also the first level. This is the second level, and this is the third level. So there are 3 levels of equations, but don't forget that each one, like R itself, is complicated. R itself is also 3 levels because you have the negation, and the conjunction, and the disjunction. So this is potentially like a 6-level or 5-level type of computation, which takes a certain amount of time to propagate. Okay. So let's go back to the next slide. And we will recognize this as exactly that equation. So when I write this out, okay, let's see whether you guys can remember, why is this becoming just BE? C in parentheses BE. How does that become just BE itself? because it's the and, okay? It's just conjunction. And remember, in electrical engineering, conjunction is represented, symbolically speaking, as multiplication. Is that okay? Any questions? Okay. What about the other one? Well, this whole thing, C blah blah blah, and then inside we have a R blah blah blah, and we have a C blah blah blah. Okay, this is the R part. Because RBE is the exclusive OR of B and E, which we have already talked about a little bit earlier, which is the overall disjunction of the conjunction of B and the negation of E, and also the negation of B and E. Are we doing okay so far with those things? Okay, we're just really expanding equations, using the logic gate representation instead of R. Is that okay? All right, the CCF, this part here, is just the conjunction of C and F, which becomes here. The carry of this component and this component is the conjunction of those two components, and that's why we have a combination like that. So are there any questions about the first row of this equation? It's nothing more than just looking back and say, okay, how did we define C? How did we define R? How do we apply those things and just expand R and C and R into logic operations? That's all we're doing. Any questions about the first row? Okay, if there are no questions about the first row, what about the second row? How did we go from the first row to the second row? In other words, how did we get from here to here? What do you think? The distributive law, right? It works in arithmetic, also works in Boolean algebra. Okay, so we take CF as the common thing that we multiply to, and then we expand so that the first term becomes B E bar CF, and then the last term becomes B bar CEF. That's all. Well, why do you think I did that?
That's a lot faster.
It is faster. Exactly. Because the negations can all happen at the same time. The negation of E and the negation of B can all happen, they can happen at the same time. So once I have the negation of B and the negation of B, everything else is already here in the first place, right? So the conjunction can all happen at the same time as well. I can have BE being computed while B E bar CF is being computed, while B bar ECF is being computed. Those can all happen at the same time. We can make multiple input conjunction gates that can operate on multiple inputs at the same time. So the conjunction results will kind of come out at about the same time, and by that time I'll be ready to do the disjunction. And once again, we can have a 3-input disjunction gate. Instead of having to have two disjunction gates, we can have a 3-input disjunction gate. So we can take all the conjunction results, combine all of them into one single disjunction. So it only takes 3 propagational delay in this case, instead of the original 5. Does that make any sense? Because the more gate levels you have to go through, the longer you have to wait for the correct result to appear as the output.
So it's gonna be more like a store machine, like a slower machine,
Like a
like a store machine.
Like a slowing machine, yeah. It's kind of like, when you go to a chemistry lab, you have all kinds of test tubes and funnels and whatnot going. So you want to minimize the number of propagational delay of your raw material to the end result that you want. So the fewer steps that are dependent on each other, the better. So you want to spread out all the operations as much as you can so that you can do as much as possible in parallel to minimize the number of delay through the system.
So like this has to go through this and this instead of 2 months in time.
Exactly. So that is the reason why we do not like carry ripple, okay? Because this result here, okay, ending up with this kind of ickish, equation, is because of the way we expand R and C from the previous slide. Well, let's go back to the previous slide one more time. What about this mess here? Oops, I just want this particular mess. The question is, can we look at this mess and use the techniques that we have been talking about and turn this into a 3 propagational delay kind of thing as well? We still have the same rules. We have De Morgan's law, we have distributive law, we have all of the other things. And the answer is yes. Okay, we can take a look at something like this. It'll be ugly, it'll be long, but it can be done. So now we go back to the next slide. So we are going back and forth between these two slides a little bit. The problem with this approach is, even though it is efficient, it is not easy to deal with manually. Remember, this is bit 2. This is the carry of the second least significant bit. We are talking about bit 1. Okay, bit 0 is trivial. It's a 0. Okay, the carry of bit 0 is trivial. This is the least significant bit, other than, well, this is the second least significant bit. What do you think the carry bit looks like for bit 63 of a 64-bit adder? Huge mess, right? And well, Intel, or AMD, they don't have to do it by hand. There are ways to do this, using a computer, okay, using a program. You can actually figure out the actual equation. But in this class, it's kind of hard to do this, okay? So what we do instead is we use the term of carry ripple, which means we don't do a closed form like this. In other words, the carry bit does not look at all the bits that are before this column, on or before this column. Instead, it only looks at certain bits. So what I'll do is I'm skipping this stuff here. I'm just going to go all the way down to here. Okay, so I'm looking at this equation here. This is basically the result of bit I. And I cannot be 0 because 0 is a special case. So from 1 to how many bits you want to deal with. Ri, okay, is the result of adding the partial result of bit xi and bit yi and the carry of column I. Does that make sense to you? Remember, I identifies which column we're dealing with. Does that make sense to you? Okay, let's see if we can draw this as a picture. So this is column I, okay? Each column is 1 bit. Doesn't have enough contrast. Xi is 1 bit from the first number. Yi is 1 bit from the second number. Okay? R, Xi, Yi is the partial sum of these two. Is that okay? And then we have a Ci, which is the carry bit of column I. At this point, I don't care how I compute Ci. I'm just saying that Ci is an input into this whole system. Is that okay? Well, then we have to add one more time. So this becomes R, the result of adding this term and this term. That's what we have. That's what we have on the projector. Is that okay? So the key concept to get to this point is I'm not expressing Ci in a big, ugly expression anymore. I'm just saying that when the previous columns are done, tell me what is the carry into this column. I don't want to deal with it. Is that okay? Now, by taking that carefree attitude, we have just simplified a lot of things. Because the result is now just the R of Xi, Yi, Ci, right? What about this guy here, Ci plus 1, the carry of the next column? Well, if you look at the equation, that's basically what it is. Because the first contributing factor is the adding of these 2 bits. If this is a 1, this is a 1, this will be a 1. That's the first one. The second contributing factor is adding this partial result with the carry of column I. That's why we have the second one, right? But because each one can be a 1, I have to combine these 2 results with a disjunction. That's how it works out. But you can apply this to as many bit positions as you want. And each column still ends up with simple equations like that. Because the only thing that we did differently this time is to say, I don't care how we come up with this. Okay? When we have this, we'll compute the final result and carry to the next column. That's the only difference. Is that okay so far? And that's why it's called carry rippling. Because when we're done with this result here, we also come up with this result here, which means the next column can now go through the same process to come up with the final result here and the carry of the next column, and so on. But I cannot start on the column until the every single column before is all done. Is that okay? So now we basically look at what we call a half adder. A half adder is a circuitry that can handle just R, Mn, M is a bit, N is a bit, and C, Mn, given 2 bits M and N. So we use exclusive OR on here, and then we use just conjunction here. So the way we draw this is we use, these are all AND gates, okay? When you look at a gate that has a straight side on one side and just a little bubble thing on the other side, it's an AND gate. This is an OR gate. Oh, hold on a second here. Tech, how do we learn this stuff here, and how can I draw fantastic schematic gate diagrams just like that? Nobody's interested.
The tool online.
Yep, the tool online is called LogicSim. Okay, so I'm going to go to LogicSim just to give you an idea of what we'll be doing for the next 6 or 7 weeks or so. Okay. I have it downloaded already, so I don't have to re-download it, assuming I know where it is. It's a Java file, it's a Java program, okay? So you just need to install Java on your computer. You don't need Linux, okay? It works just as well in Windows. And let's see, is it here? Yep, it is here. If you want to start it off from the command line, you just say, Java, assuming Java is on your regular path, -jar, and then the path to the jar file. Jar, J-A-R, stands for Java Archive, okay? It's basically a zip file with individual files inside. So you just press the enter key and it starts up. Unlike most other things that I do in this class, this is all GUI. Some of you look at me and go like, why is that an important statement? And if you have taken my classes before, then you go like, oh, good, it's all GUI, not the command line. Because I like to do things in command line. This is not. This is really easy. So what you do is you look at this, and the first thing you want to get familiarized is the help. Because not only does it give you a library reference, which explains every single gate that is already implemented in the library, it will give you a tutorial. Okay? A tutorial teaches you exactly how to use this particular program. I could not have written instruction as complete as what we already have here. So this is your primary source of information of learning about gates and how to use this particular program. So the next thing I'm going to do is to just kind of show you briefly how we can construct, a gate diagram like this one. Okay? So you take these tools. This is just really a shortcut because you can also get to those by expanding gates. Okay, so you can pick out these things too, and they have names, next to them. So you can see this is an AND gate, this is an OR gate, and so on. So we'll just go ahead and replicate the picture that we have earlier. Okay, so we pick out an AND gate here, and you go like, wow, this doesn't look like the other gate. Well, look at the attributes. Look at the attributes of this particular gate. The facing basically is saying, okay, what is the output relative to the input? It's facing east, which means the output is on the east side, the input is on the west side. It's okay, that's not a problem. Data bits is good, okay? You can actually work on multiple bits at the same time. We want to shrink the gate size to narrow, so it's smaller. We also don't need 5 inputs. So in this case, we only need 2 inputs. So we can shrink it to 2. So now it looks more like what we have. And if you are saying, I cannot see anything, I cannot see the 2 input and the 1 output, well, we can magnify. There we go. Okay, so now it's a little more clear. And then we go back to the picture and go like, oh, there's a bubble here. What do you think that bubble means?
Negated.
Negation. Okay, so that's negation coming in. Okay, so how do we do that? How do we draw that little bubble? Once again, you want to look at the properties of the gate itself. It gives you the option of negating the top, which is this guy here, negating the bottom, which is this one here. They are independently controlled. So if I want to replicate the picture that I have on the slide here, which is the bottom one getting negated, I can just negate the bottom one. Is that okay? All right. And the next thing I want to do is to go like, I have 1, 2, 3 AND gates. They all have about the same configuration with some minor differences. So what you can do is you can select one, Control D to duplicate. And Control D to duplicate one more time, and then you can just hand edit each duplicate so that they are basically what you want in the end. So now we have 3 AND gates, and they are kind of in the configuration that we want. Are there any questions? Okay. Now we want to specify the input. They're basically like parameters to a function. In this case, we have 2. We have M and N as input pins. These are pins, okay? The square pins are input pins, which means they specify something to the bunch of gates that you specify. The circles on the right-hand side, they are output pins. Okay, so they're input pins and then they're output pins. In the tool, you can see that there are input pins and there are output pins. So you can just drag, select, paste. We only have 2 input pins, so we just drop 2 of these pins in. For each pin, you can kind of control its position. Each one also has an optional label. Like this one, if you want this one to be bit M, then you can just type in M here, and I want this one to be bit N, and we have bit N. Is that okay? Going back to the picture here, you can see that bit M is connected to the input of this gate here, the negated input of the second gate, and also the input gate of the third one. We can see they're connected because of the dots here. So now you can do the same thing. Just drag and drop. Okay, drag from the beginning, drop at the end, and we can do the same thing here, and the same thing here. With this one, pretty much the same thing. Okay, and you can see that this intersection doesn't have a dot, which means it's a flying over. So these 2 wires are not really touching. One is flying over the other one. If you don't see a dot, they're not connected. And we have another one, which is right here. Are we doing okay so far? Going back to the picture, we have an OR gate here. So go to here, it spells out this is an OR gate, or if you want, you can also drag an OR gate from here. Once again, it's too big, so we want to shrink it to a narrow size, 2 input, like so. And if you don't really care about it looking symmetric and nice, you can just do it like that. Okay. And now we can specify the output, because now we have 1 output from this gate and 1 output from this gate that they are not connected anywhere. So now we specify the 2 outputs. Output pins are the circle ones. Okay, so we put one here, and then we'll put the other one maybe down here. It's nice to label these. This is our carry out. This is the result or the partial result of a half adder. Drag and drop, make the connections. And now we have a half adder. Okay, so we're implementing both the function R, which is the top part, and also the function C, which is the bottom part. Yep.
In this program, can you give it power and like simulate it?
Yep, it's called Logic Sim for a reason.
Okay.
Right? Okay. So how do we do it, get it into simulation mode? Because it does say simulate, right? How do we activate it?
How do we do that?
Well, we use this thing here. Okay, this little hand here. Change value within circuit. It's already simulating. Okay, it is actually computing right now. Because if the input to this thing is 0 and 0, the outputs should be 0 and 0. So it's working already. The question is, how do we change the input from 0 to 1 and see if it still works? That's the question. So to change the values, you have to change the tool because we are no longer editing and adding wires. We are actually changing the value. So click this tool and go back here. Is this correct?
Yes.
Adding 1 to 0 ends up with a result of 1 and carry of 0. Works out. What about 1 plus 1? We end up with a result of 0 and a carry of 1. Is that right?
Yep.
What about the last combination, which is a 0 here and a 1 over there? It is still correct. Okay? So this is how you draw, simple, gate logic stuff. Are we doing okay so far with this? Okay. I didn't have time to specify a homework assignment, so I'm not going to give you guys an official homework assignment. But the purpose of the homework assignment is I want you guys to put together a 3-bit adder, but without using carry ripple. Because it's too easy to do it with ripple into carry bit. So I want you guys to actually expand out the equations and figure out the big mess thing. So that's kind of what I want you to do, but I don't want, you can experiment, you can kind of go ahead and try it out, okay, in today's lab time, just to figure out the tool, okay? But don't turn in anything, don't save the files, because it's really just for exercise, okay? But your homework assignment is going to be a 3-bit adder, but without using carry ripple. So you kind of have to expand all the equations and use, you'll end up with a lot of gates with a lot of inputs. Some of those will be negated, okay, but not a lot of levels of gates, okay. And so that will eventually be your homework assignment. I don't have it written yet. So at this point, it's really just an exercise. The other thing you can do that is really cool, okay, about this tool is you can look at this as kind of like program steps, okay? You can turn it into a function. Okay, now that part is really cool because if you need to replicate this design like 20 times over, you don't need to copy and paste it. Okay, what you do is this. This is the main quote-unquote circuit that we are dealing with. Change this name. Change it into half adder. So now it is HA. Well, it looks like just a name change. But one thing you can do is right-click on HA and you can edit circuit appearance. So now it looks like a little chip, right? And as a little chip, if you want to, you don't have to, you can label it. So you can label, I think it's one is M. One is N, one is R, which is the result, and one is C, which is the carry. Now, if you say, but I have too many input pins and too many output pins, I cannot remember which one is which one, it's really nice because if you click on one, it shows you a picture in a picture at the lower right-hand corner, and it highlights the actual pin in the original design. So that way you can be reminded what this pin is really about. So this is M, this is N, this is C, this is R. This becomes a subroutine. This is what we call encapsulation in programming because you're now hiding the details of how a half adder actually works. Okay, I don't know what gates are actually being used. I just know that there are 2 inputs and there are 2 outputs. Okay, and what you can now do is you can go back to project and you say add circuit. Well, we'll name this one maybe FA for full adder. Okay, so a full adder makes use of, guess what? Well, the other one is called a half adder for a reason, right? How many halves do we need to make a full? Okay, so we stick one here and we stick one here. You can see how this becomes kind of like a subroutine because now we can quote unquote call the subroutines. We can say, oh, we want here, and one over here. Now we can make connections between these two to make a full adder. Okay. Oh, how do we make a full adder based on the equations that we have talked about so far? So let's say M and N are the actual input pins. Okay, so these are representing the bits of the two numbers that we are adding. So, well, it kind of makes sense that these two have to go to a particular half adder. Okay, that part we know. What about the input into the second adder, the second half adder?
The RC, the output.
The R goes to one of the input of the second half adder. Okay. And I'm going to write it kind of like this way. Okay. Even though M and N are really symmetric, I'm not going to do it that way because M has to hook up to something else. What is the other input into a full adder?
To the half adder.
Look at this picture here. You got X, you got Y,
Oh,
right?
To the
This
carry.
is exactly the carry in, right? This is the carry from the previous column. Remember we said, we now take a very, very carefree attitude of we don't know how or who comes up with this, but it becomes an input into this column, right? Now it becomes an input pin. So now we make another input pin. That becomes carry in. It's the carry from the previous column. Okay? Now in a proper design, all the outputs and all the inputs should be used. And we have quite a few that is not being used right now. What about this R? Where do you think this goes? Okay, that R is representing this guy here. This is the final result of this entire column. Okay? So that means it goes to its own output pin, like so. Now we have two carries that are kind of like dangling. They're not really connected to anything. One is the carry from adding these two bits. The other one is the carry from adding these two bits. What should we do about those two? How did we come up with this guy?
So you do C plus.
Okay, we have the carry of this coming out from the first C. We have the carry of these two coming from the second C of the second half adder. How do we combine those two into one single output? What gate do we use? OR. OR is correct. So now we use an OR. And just kind of simplify the design a little bit. Like so. Yeah, things are not really lining up. I'm not artistic. At the least. There we go. So now we have a full adder. X is one of the input to the far left. Y is one of the other input to the far left. The middle input is the carry in. The final result is the top output pin to the right hand side, and then the carry out is the carry or the bottom output pin to the right hand side. Now in previous in reincarnations of this class, people have to do the full adder, and then we have to make a 4-bit adder out of the full adders. That's not what we are doing this year. We're doing a 3-bit adder the long way. Okay? But what I'll do is I'm going to implement the 3-bit adder using this technique, and then we can compare the timing. So we can actually see how much time it takes for this approach to finish a 3-bit by 3-bit add, as opposed to the other way, which is the long, kind of more complicated way, but it's going to be faster. So that's what we'll do this year. Are there any questions at this point about how to use LogicSim, what it is about, how do I get more information about it, that sort of thing? No questions? All right. So if there are no questions, I'm going to end the lecture part. There's no structured instruction, during the lab, but for people who want to, take your first step at the 3-bit adder, not using carry ripple, you might want to do it in the lab just to get used to the tool, get used to, the concept, and ask questions related to what we have just learned today. Which is not a whole lot, except Base 2 is better than base 10.
Do you think we should teach base 2 to first graders instead?
Absolutely.